Okay, so here we have question 2, which is moment of force about an axis, um, which is also section 3.2. We're going to solve this one a lot like what we did for question 1, actually. So first, what we're going to do is we're going to be grabbing our points. So doing that means we're first going to start off with A. We're going to start off with A. We're also going to do we're going to do E. We're going to do, actually, hold on. We're going to do A, D, E, F, and G, because we actually don't end up using B and C. So point B, there's absolutely nothing that heads to it. When we do this out, we're going to be using the cables, which is why we need EF and EG. We're going to need DA because that's where we're finding the diagonal. And we're going, and we're not going to need C because while it does have a force there, it's not going to matter that the force is there. It's simply, it's not going to be figured into the moment equation that we're going to use. So therefore, we're going to just grab these points. Now, from here, point A is at the origin, so that's simply just 0, 0, 0. Now we grab D, which is over here in the corner, which we can grab the 12 and the 5, and it's not, doesn't have any vertical to it, so that would mean it's going to be 12, comma, 0, comma, 5. Now we're going to do E. E is very close to D. It's actually only just 6, 6 backwards and closer to the Z-axis, which means that it's actually going to just be 6, comma, 0, comma, 5. Now we're going to do F. Now F we are given the point for. It's 0, comma, 3, comma, 2. Now we do G, and if you look at G, it's 7 on the x-axis, followed by, it has a vertical of 2, if you notice that here. So 2, comma, and then it doesn't have any motion in the Z direction. Well, it does, but the point G is not in the ZX, it is on the X plane, so it doesn't have any area in the Z, which means that's 0. So what we're going to start off by doing is we're going to calculate out our, we're going to start working on getting our lambdas again, just like what we did in question 1. However, we only have 2 cables this time. We have EF and EG. So I'm going to start off with EF. So EF equals, I'm going to do it, keep in mind this would be F, the F sub F, point F sub X. So that would be 2 minus E sub X, which would be 6, comma, sorry. My bad on that one. It's not 2. I was thinking of the wrong thing. F is 0 in the X one, so that means it's 0 minus 6. My bad. I made a mistake. Then we go on to the y-axis. And now here, F is actually at 3, while E is on, it doesn't have any direction in the y, so that would be 3 minus 0. Now we go on to my z-axis. So here, this is where I got a little confused. It's actually supposed to be 2, and I accidentally associated that with x. So I'm going to do my 2 minus my e value of 5. This equals then negative 6, comma, 3, comma, negative 3. So now I'm going to calculate out my E bar. My magnitude of E. That's what I meant. My bad. Magnitude of EF. which equals, actually, hold on, I'm just going to rewrite this. My magnitude of EF, which equals the square root of -6 squared plus 3 squared plus -3 squared. So when I do this, I end up getting the square root of 54, and that equals 7.348. Now I'm going to use this to calculate out lambda. My lambda EF equals -6, 3, -3, all divided by my magnitude of EF, which is 7.348, because, and that is the equation that I would use for it. So now when I multiply out and do all my division for each point, I'm going to end up getting -0.816, comma, 0.408, comma, negative again, because it's -3, 0.408. So now I'm going to work on EG. EG. Now this equals, when I do the point, I'm going to do the same thing as what I did before. So G occurs at 7, so 7 minus 6, comma, 2 minus 0, comma, 0 minus 5. This equals 1, comma, 2, comma, -5. Now what I'm going to do is I'm going to find the magnitude of EF. When I find the magnitude of EF, I'm going to do 1 squared plus 2 squared plus -5 squared. This equals the square root of 30, and which that equals about 5.477. So given that, now we're going to calculate out lambda. Lambda is, I'm going to take my EF value, sorry, my EG value. Didn't mean to write EF here. That was supposed to be EG. EG value. So I'm going to do my 1, comma 2, comma -5. And I'm going to divide that by my magnitude of EG, and when I which is 5.477. So when I do this all out, I get 0.183, comma, 0.365, comma, -0.913. And that would be my lambda for EG. So what I'm now going to start doing is I'm going to try to solve for my tensions, because I want to find the moment about the diagonal dA of the force exerted by cable EF. Now, dA would be this. That's going to be dA. However, first, we have, in order to find that using EF, we actually have to solve for EF. So that goes back to using what we did in the last video. So that means I'm going to start off with my sigma. I'm going to do f sub x again equals 0. So there's only two cables this time, and I know that this negative 200 here is directly downwards. So that means there's going to be no effect of it in the y-axis. So when I do this, though, I'm going to take my tension in cable EF, which I find to be negative 0.816, and I add my tension in cable EG, which I find to be times its lambda. So I don't actually have the tension solved for yet, but it's multiplied by its lambda of 0.183, and I find this to equal 0, because those are all the forces in the x direction. Now when I solve this out, I'm actually going to solve, because I want to try to get TF, the tension in cable EF. So what I'm going to do is I'm going to solve for TEG here, so that way I'll have my my next equilibrium equation all in terms of TEF. So that way I'll get my TEF answer, and then I can start working on my next problem. In the next part, which is finding the moment. So I'm going to use my I'm going to use my sigma E sub y, because I want to use this 200, so that way I get a nice value for it all. And I don't just have it equaling 0 and being really inconvenient. So I'm going to do sigma f sub y equals 0. And that will give me my t. Oh, sorry. Oh, my bad. I haven't solved out for this yet for you. So when we do this, we're gonna flop the sides. So this is gonna go to the other side of the equation, which means I'm going to get TEG times 0.183 equals 0.816 TEF. Now I divide by my TEG, so that would give me TEG, the value that is the before TEG, not TEG itself, which equals, which then gives me 4.472 TEF. Now that I have that direct connection, I can then go to my second equilibrium equation of f sub y, have that equal 0, and I can use substitution in this, so that way I can get it all in terms of TEF. But first things first, we're going to write it out before substitution. So we're going to do TEF times its value in the y direction, which we find to be 0.408. Now we're going to add, well, I'm going to move this over some so we just have some more space. Okay, that didn't want to work. There we go. And now we're going to add our TEG. Now keep in mind, we will substitute this out, but we're not yet. And we're going to grab our value in the y direction of 0.365. Now, because we know this 200 here, back up here at the graph, graph, and that's downwards and only in the y direction, so that means we're going to do minus 200, and this all equals 0. So now what we're going to do is we're going to do our substitution. So that tells me that 0.408 TEF, and we're also going to add this to the other side, just that way the left side of our equation is all in TEF. And that's our only values there, and its coefficient, of course. Plus 4.472 TEF times, of course, the 0.365, because we can't get rid of that, and this equals 200. Now, given this, I'm going to first multiply out that 4.472, and I'm going to multiply that by the 0.365, and then I'm going to add my and then I'm going to add onto the 0.408 onto that, which then gives me, so basically I end up getting 0.408 TEF plus 1.632 TEF. This equals 200. Now I'm going to combine like terms. This isn't a negative. This is point, just to be clear, which ends up giving me 2.041 2.041 TEF equals 200, which there means that TEF equals approximately 97, that's a bad 9, 97.980 newtons. And if you're really curious, we could take this value and move it back into our equation up here to solve for TEG. However, we don't really have to in this one because we simply are looking for the force that my TEF value applies to dA. However, if you were curious, when you end up multiplying that out, you'll end up getting TEG equals about 438.178 newtons. However, this value ultimately does not matter. So we're only going to focus on that TEF. So now that we have that, I'm going to solve out and get my actual lambda. I'm going to do my lambda EF, and I'm going to multiply it by my TEF value, and that will give me the value I need for my moment problem. So this, when I do that out, will be negative. It's going to be 97.98 times negative 816, comma 0.408, comma negative 0.408. When I do this out and multiply these values out, I end up getting approximately, of course, negative 80, comma 40, comma negative 40. Now, while I understand that when you multiply that out, you're going to get like negative, for the x value, you're going to get like negative 79.9 repeating. I'm just simply rounding that to 80 because there's a lot of 9s, and that essentially equals 80. The difference in it is because we rounded earlier and didn't use the exact values that we got. If we used the exact values we got, we would have gotten just a plain 80, a plain 40, and a plain negative 40. But now, before we go in, we're going to actually apply, we're going to actually end up applying a direct property that we have to get our moment in line DA, which, if you didn't know, it would be our moment of dA equals, it takes my it takes lambda dA, and I do a dot product times r of dE times cross product our value here. So when I do that, it'll be cross product times negative 80, comma 40, comma negative 40. So that means that we have some more points and stuff to solve for. So that means we're going to have to go back to up here and grab all of those points that we used, but we didn't calculate out into EF. So first things first, let's start off with RDE because it's a pretty simple value to calculate. So RDE. So this actually just pretty much equals what changes between my between point D and point E, which if you remember is, so this is the same as pretty much writing just DE, which equals, if we go up here, it would be 6 minus 12, comma, 0 minus 0, so I'm just going to put 0, comma, 5 minus 5. Now, when I do this out, I'm going to end up getting negative 6, comma, 0, comma, 0. And that's what we get for that. I like writing it in this form. You can also write this as just negative 6i. However, I like writing it in this form as it just makes it easier when I go to do cross products and stuff. So that then brings me to calculating out lambda dA, which is a little more challenging. So first we have to calculate out dA, which when we do that, it's pretty easy because A is 0, 0, 0, which means dA is simply going to be the just the negative of D, which means because it's just going to be 0 minus 12, comma 0 minus 0, comma 0 minus 5, which means that essentially this will just end up being negative 12, comma 0, comma negative 5, because it's just the reverse of it. So now I go into calculating my my magnitude of dA, which ends up equaling 12, the square root of 12 squared. While I'm aware it's negative 12 squared, however, when you square a negative, it ends up being positive. So I'm just going to write 12 squared plus 0 squared plus 5 squared. And yes, I'm aware that it's negative 5 squared. However, when you square a negative, you get a positive again. So this actually works out very conveniently though, because so 12 squared is 144, 5 squared is 25. When you add those together, you get 169. And that equals 13, which is pretty convenient. So now when I do this out, I'm going to calculate my lambda dA, which gives me negative 12 divided by 13, comma 0 divided by 13, comma negative 5 divided by 13, which when I do that out, it equals approximately 0.923 negative, of course, comma 0, comma comma negative 0.385. Now I'm going to solve for my m of dA. M sub dA equals my lambda dA value, which I just calculated here. So that's going to be negative 0.923, comma 0, comma negative 0.385 dot product of my cross product here, of negative 6 comma 0 comma 0. Well, I'm aware you can write that as negative 6i. However, I write it this way because it's just easier for me to do cross products and dot products for. Cross my value up here of negative 80 comma 40 comma negative 40. So when I do all of this out, you end up getting do your cross product and use your dot product of your cross product, and there's a convenient formula for this though. So I'm going to simplify this a little bit because as you do it out, you're going to end up getting, it ends up equaling negative 0.923. And now when I do my cross product, because these two values here are 0, that means that no matter what I multiply by, I'm not going to have any effect in the x-axis for my cross. So that ends up just being times 0 minus 0. And then it's minus because that's just how the formula works. And here, though, however, on this one, we have our lambda equals 0. So that's going to be 0 times some value. However, it doesn't matter because, well, it's multiplied by 0. Then you go back to addition, and you add negative 0.385 times my cross product of when I do my x value here, my x value times my y value, which ends up giving me negative 240, subtracted by my x value here, times the y value, which gives me 0. So when I multiply this out, it ends up working out where this gets canceled, and I'm just left with the z direction. However, it's no longer assigned in the z direction. It's just overall. It's overall because when you do a dot product, you actually get a scalar result instead of your vector results. So when you do that out, you end up getting, you end up getting negative 0.385 times 240. This means that my moment of dA equals approximately, because it's negative times negative, it's going to be a positive answer, 92.308 newtons. And that is the answer for question 2. Yeah, there you go.